future decades. It's the end of the road for transport as we know it, and the question is, what will come in its place? "30 years from now, oil reserves will have run dry, there'll be no fuel, the combustion engine will be dead, and the conventional car condemned to the scrap heap." A bleak future? Well, perhaps not. A new generation of vehicles could save us from this grim fate.
I like this car. It's very quiet. The response of the accelerator is very good.
This car drives like any other. Its top speed is 150 kilometers per hour, and it can travel some 450 kilometers before it needs to refuel. But when it comes to the engine, it has more in common with the space shuttle than its petrol-powered cousins. Ever since the car revolution took off with Henry Ford's production line, vehicles have relied on the internal combustion engine. As we start the 21st century, it's still at the heart of the car. The technology has been tweaked and stretched beyond recognition, but there is a limit beyond which this dirty, smoky machine cannot be taken. And when the fuel runs out, there'll be no place for the internal combustion engine to go. And that's where the Neckar 4 comes in. It's the latest in a series of alternative power cars to be developed by Daimler Chrysler. It's an electric car, but unlike any that has been seen before. Until now, these cars have been weighed down with heavy batteries. They can manage only low speeds over short distances and need to be recharged for long periods. So Daimler Chrysler decided to take a different approach. What if the electricity was made on board the car itself? And what if it could be generated using the most abundant fuel of all, hydrogen?
We need here no fossil fuels. It means so long we have water energy, the sun is shining, we can produce the hydrogen. And in the same time we don't pollute the environment.
The electricity is made inside a fuel cell, a box where hydrogen and oxygen are combined to make water. During the reaction, energy is released, electrical energy that can be harnessed to drive the car.
When you push the accelerator, the hydrogen goes through this tube into the gas channel, and it provides our fuel cell with hydrogen. From the other side, we supply the oxygen from the air, and we let it react it inside the fuel cell to electricity.
Fuel cells are simple, efficient and pollution-free. Powering them requires only hydrogen obtainable from water and oxygen from the air. Which is why one country with plentiful supplies of both is planning to convert its entire transport system to fuel cells. High in the North Atlantic is the country of Iceland. A clue to why they're thinking so radically can be found on the farms of men like Olaf Eggersten. His farm has its own generator, the cowshed is air-conditioned, feed is dried, and there's even a hothouse where he can grow Mediterranean fruits. And the energy to do this costs next to nothing.
The land here has many resources. It's just a question of making the most of them.
Iceland sits on the point where the continental plates of Europe and America meet, creating a geothermal hotspot. Steam and water bubble out of the earth, providing both heat and energy to drive turbines. Elsewhere, there are abundant waterfalls from melting glaciers, providing non-stop hydroelectric power. Iceland already generates 2/3 of its domestic power from these waterfalls and geysers, yet this uses just 1% of the country's natural resources. So, these two men, Hjalmar Arnason and Bjorn Skulason, plan to tap this energy source further and produce hydrogen from water, taking Iceland, and perhaps the rest of the world, out of the carbon economy completely.
With respect to all the sustainable energy we have here around us and the manpower we have in Iceland, I believe that Iceland will become the first hydrogen society in the world.
Arnason is a member of Parliament and a visionary, and he heads a committee that is dedicated to making his dream a reality. He and Skulason have set up a company to draw up the blueprint for Iceland's future, and perhaps the future for the rest of the world. And they've been captivated by the Neckar project's success.
The changes with fuel cells could be, to begin with, the buses and the such vehicles. Then you have passenger cars developing, and hopefully the automakers will be mass producing fuel cell vehicles in 2004 or 2005. Hopefully, shortly after that, we will have mass production of ships which could be powered by fuel cells. In the long run, we could also power airplanes with fuel cells or with hydrogen, since already all space shuttles and so on are powered by hydrogen.
To fuel this ambitious plan, Iceland is going to need to produce hydrogen on a large scale. But with nearly unlimited geothermal and hydroelectric power to hand, it'll be in a position to manufacture the gas cheaply and in bulk. And that's not all.
What is more, we see that within not many years, we might start exporting, and we will pretty soon start exporting hydrogen from Iceland to the international market and obviously make money. Perhaps we will end like Kuwait of the North. That is our future dream.
Within 20 years, every car, truck and bus in Iceland will run on a hydrogen-powered fuel cell. And it may not be too many more years after that before we're all driving cars with fuel cells instead of engines and Icelandic hydrogen in place of Middle Eastern oil. Hydrogen-powered cars may not be the only new way to get around. Japanese scientists may already have found the ideal energy source for the transport of the future in the form of a powerful natural phenomenon. It is one of the four fundamental forces of nature generated by molten metal at the core of the Earth. And now it's being used to push a train along a track. That force is magnetism. These giant magnets power the fastest train in the world. They're so strong that they have to be superconductive and cooled by hydrogen. They're coupled with magnets on the track, which attract and repulse to pull the train along. The result of all this high-tech engineering is a train that could travel from London to Paris in less than an hour.
We've developed the maglev with a top speed of 500 kilometers an hour for commercial use. This system's target is to compete with domestic flights, which connect the big cities. The maglev system will cut the journey time between the cities of Tokyo and Osaka to 1 hour, quicker than an aeroplane. I'm sure this system will be adopted in the future.
If this sounds familiar, it's because it is. Magnetic trains have been around since the 1960s. The desire for high-speed intercity links pushed everyone to look for alternatives to the traditional rail system. A floating train seemed the answer. Using magnets to levitate the vehicle above the track removed friction, and the electromagnetic repulsion that drove the train forward was pollution-free and virtually noiseless. It may have been groundbreaking technology, but will it ever be promoted from test track to transport network? In 30 years of working with maglev, Professor Tony Eastman has closely followed its development.
Maglev has been around for a long time, but it's not yet really found application. I think the costs of it are such that people have been very hesitant to commit to an implementation.
In the meantime, maglev was still being tested, and tested, and tested, without ever making the leap to fee-paying customers.
The reason was cost. Maglev is exceptionally expensive, and the comparatively cheap traditional trains were becoming almost as fast.
High-speed rail systems have really closed the gap. They have now advanced to 300 kilometers per hour and can go to 320 or perhaps 350 kilometers per hour. I believe that high-speed rail is a more economical system, while not quite so fast. The increased costs that one has to pay for maglev are just not worth the reduction in trip time that such a system could offer.
Super-cooled, super-powered magnets may provide speed, but at a price. The technology was simply too expensive to be of practical use. But now, maglev may have found a new lease of life, not at 500 kilometers per hour, but at 50. Congestion and pollution plagues every modern city. Roads cannot cope with the numbers of cars and buses, and metros are oversubscribed. What our cities desperately need is a new high-tech public transport system.
Maglev also, I think, does have a lower speed application. Japanese company HSST has got, in my view, a technology which has got nice characteristics for urban applications. It's the type of system that could be used for downtown people movers to provide a linkage of downtown buildings.
It may not be as swanky as its big brother, but HSST works on exactly the same magnetic principles as its high-speed sibling. It turns out that all the characteristics developed for speed are also useful in an urban transport system. Gripping the track provides safety. Magnets are non-polluting, and magnetic force can even cope with the most extreme weather. And because it's slower, it doesn't need powerful and expensive magnets, but smaller ones that can be laid on the track for a fraction of the cost.
We have developed it as a high-speed urban transportation system with a top speed of 100 kilometers per hour. As it's floating, there is very little noise or vibration, and there is no pollution, which means it is an ideal transportation system for the city. HSST is operating trains with 3 carriages. These trains do not have drivers. This plan has already been put into effect, and I believe it will be a very important transport system in the 21st century.
In 20 years' time, I think that low-speed maglev rail systems will be really providing urban people mover type systems.
With commuters in some parts of the world already spending up to 3 hours a day stuck in traffic, HSST could offer a unique solution to gridlock. What started as an expensive experiment may yet prove to be the answer to our urban transport problems.
However smart these ground transport solutions, they alone won't be enough to solve future transport problems. Perhaps it's time to look to the skies. But today's aircraft won't be able to cope with the ever-increasing number of passengers and cargo, and the high-tech alternatives, the rocket ships and space planes we've been promised, are still firmly in the realms of science fiction.
Which is why some scientists believe we may already have the solution right under our noses, in the shape of a 100-year-old idea. the airship. Quiet, spacious, environmentally friendly, and able to carry hundreds of passengers or tons of cargo. A new era in giant airships is beginning back at the Zeppelin factory in Germany with the revolutionary LZ N07.
The flight test phase is over, so that means we know everything of the behavior of the ship, and also we improved, of course, certain parts of the ship, and we are ready for certification now.
Zeppelin have used space-age materials and state-of-the-art engineering to construct their lighter-than-air craft, which they predict will take the transport world by storm, just as airships like these did decades ago. Most of these early airships were rigid, with an elaborate internal skeleton of heavy metal beams. Their huge envelopes were filled with the lightest gas, hydrogen. But this design was fatally flawed. When the Hindenburg exploded into a fireball, it was the beginning of the end for the airship. As a result, today's airships, nicknamed blimps, have no practical use for transportation and are seldom more than floating billboards for advertising. Their simple structure is non-rigid, where only the internal pressure of the gas maintains the shape of the envelope. Zeppelin have pushed the boundaries of airship technology even further. Their new design is more than just a bag of gas, like a blimp, and lighter and more manoeuvrable than rigid airships. It combines the best of the past with the best of the present to create a revolutionary design for the future. Dr. Strata, Zeppelin's CEO, explains.
This is a totally new approach, of course. The old Zeppelin was a rigid structure. The disadvantage of this structure is, of course, the weight. And if you're going to the aviation, always weight is a critical parameter. And therefore we looked for extreme lightweight design and construction. This is carbon fiber, and that's the lightest material. And that means most of the parts are used from this or made by this material. And the rest, where we need another stiffness parameters, is made from very light aluminium, of course. Everything which is common in aviation and space industry. I ask always people visiting the company what's the estimation of the weight, and their estimation is 500 kilos, 700 kilos. In reality, it's 95 kilos. So that means you can see the differences.
The Zeppelin's revolutionary design isn't just light. Its new propulsion system gives it greater safety and manoeuvrability than ever achieved before.
We designed a new propulsion system, and you see propellers, and we have 3 engine groups on both sides and at the rear end. And these propellers are swiveling propellers, and that means we can start and land like a helicopter.
This increased manoeuvrability, together with a state-of-the-art cockpit, makes the once dangerous takeoff procedure now both safe and simple.
After we have the clearance from the tower, then we tell the crew chief that we're ready to go off mast. And all these handles then at that time are forward here. And then as we're ready to take off, we lift the vectors and give power with these. Then the ship lifts almost vertically.
Zeppelin's new airship can transport 12 passengers at cruising speeds of 80 miles an hour. Future models could carry many more. But when it comes to solving future transport problems, Zeppelin's new passenger model is just the beginning.
The real challenge for the future is cargo transport. If the burden of moving goods and machinery around the world could be taken off the roads, it might make travelling for the rest of us much more bearable.
Could an airship, larger, sleeker and faster than ever before, be the answer? It seems so. Brand Air Force Base in the former East Germany, once home to Russian fighter aircraft during the Cold War, is now a centre of airship excellence. Here, engineers have plans to build the biggest and most ambitious airship yet. The cargo lifter will carry payloads of up to 160 tons. That's the weight of a jumbo jet.
The cargo lifter is the basic idea to combine an airship with a crane system. The major job they will do, they will transport heavy lift outsized goods. Just to give you a comparison, the size of the goods is about 50 meters long, 10 meters wide, 10 meters high. So this is a three-store building actually, what we can transport. So we are focusing on these heavy machinery parts out of the power plant industry, civil engineering industry, out of the oil industry. So we can transport high volume goods, what's not possible today.
The cargo lifter will be so big that a special purpose hangar has been designed to house the first two models and to serve as a production facility. It will be the largest hangar on Earth. But before the full-scale cargo lifter can be produced, a smaller prototype model must be put through its paces to see if the new technology will work. This is the 1/8 scale model of the cargo lifter, affectionately named Joey.
We are very satisfied with the flight tests we have done so far. Joey serves many important purposes for us in the development process and in the construction process of the cargo lifter, because it was a kind of rehearsal for us.
Joey's success has allowed the engineers to begin production of the full-scale model. These airships will provide an environmentally friendly, efficient and elegant way of ferrying vast cargoes around the world. Relieving the pressures on ground transportation could yet see the return of giant airships to our skies.
Decades. It's the end of the road for transport as we know it, and the question is, what will come in its place?
"30 years from now, oil reserves will have run dry, there'll be no fuel, the combustion engine will be dead, and the conventional car condemned to the scrap heap." A bleak future? Well, perhaps not. A new generation of vehicles could save us from this grim fate.
I like this car.
First century, it's still at the heart of the car. The technology has been tweaked and stretched beyond recognition, but there is a limit beyond which this dirty, smoky machine cannot be taken. And when the fuel runs out, there'll be no place for the internal combustion engine to go. And that's where the Neckar 4 comes in. It's the latest in a series of alternative power cars to be developed by Daimler Chrysler. It's an electric car, but unlike any that has been seen before. Until now, these cars have been weighed down with heavy batteries.
It's very quiet. The response of the accelerator is very good.
This car drives like any other. Its top speed is 150 kilometers per hour, and it can travel some 450 kilometers before it needs to refuel. But when it comes to the engine, it has more in common with the space shuttle than its petrol-powered cousins. Ever since the car revolution took off with Henry Ford's production line, vehicles have relied on the internal combustion engine. As we start the 21st to make water, during the reaction, energy is released, electrical energy that can be harnessed to drive the car.
When you push the accelerator, the hydrogen go through this tube into the gas channel, and it provides our fuel cell with hydrogen. From the other side, we supply the oxygen from the air, and we react it inside the fuel cell to electricity.
They can manage only low speeds over short distances and need to be recharged for long periods. So Daimler Chrysler decided to take a different approach. What if the electricity was made on board the car itself? And what if it could be generated using the most abundant fuel of all, hydrogen?
We need here no fossil fuels. It means so long we have water energy, the sun is shining, we can produce the hydrogen. And in the same time we don't pollute the environment.
The electricity is made inside a fuel cell, a box where hydrogen and oxygen are combined